Welcome to another tutorial of the thermal system design class. In this tutorial we're going to go into the solutions for the turbulent flow over a heated cylinder. So we're going to check onto the velocity, temperature, and pressure contours. We're going to create plots for the velocity, temperature, and pressure at different distances down the stream flow of our problem. We're going to calculate the surface heat transfer coefficient and the total heat transfer rate. So from last tutorials, we know that if we go to surfaces, we click on meshing, and we go to new surface, and we click on isosurface, we're gonna have different options here on surface constants, and we select the meshing. It's gonna give us the plane that is the plane that we want to select as the normal plane, which we're gonna create our plane for the contours. So we're gonna select the C plane, and let's call this plane 1. Plane 1. And when we compute this, it's gonna give us the edges, the top and the bottom edge of the domain. If we select our ISO value to be 0, then it's gonna create a plane at the middle. We create it. We can see here in our mesh display that is giving us the option to show plane 1 selected, and we can see that our plane 1 has now shown on our domain. Let's deselect the symmetry wall just so you can see a little bit better. So we can see now that our plane has been created. We can close this. If we go to contours, now we can actually create our velocity, magnitude, or our plane 1. Save and display. Change the orientation for this. And there we have our contour for the velocity. You can even change if we wanted it banded or we wanted more smooth. You can change the color mapping. I'm going to change it to similar color that we had on our previous problem, which was the laminar flow. You can change other things here inside of the color map. We can close this. Let's also move our color assignment to the bottom. And instead of exponential, let's have it as float. Let's close it. So this is our velocity. So we compare it to the results from last time. We go to we can see that on the laminar flow, because it takes more time because we have less velocity, it takes more time for the velocity to develop down the stream, that we have this whole area creating this whole area of our velocity magnitude in which it increases. In this case, our area is not as large. That is because our velocity is bigger, then it's not developing as fast as in this case. So it's one of the solutions that we can compare from this. We can close this. We can also check the other options, which is the temperature. And obviously you can go to File, Save Picture, and you click on Save. It's going to take you where you want to save it. You can name it however you want. I'm not going to change every single one of them. You've learned how to do that. And if you don't, you just click on here and you'll create it, and you'll take it where you want to be saved inside of your computer. You can name it here, velocity turbulent. You just click OK. It's going to be the same thing for the temperature and the pressure. So now if we select the temperature, save and display, we can see how our temperature is bigger around the downstream of the cylinder, this area, We can also compare this to our previous results. We have the same case, which the temperature didn't develop as much. Also, we can go to pressure, save and display. This is what we obtain. So now we can create the plots for the velocity, the temperature, and the pressure at D, 2D, and 3D. So we can close this. We can go again into meshing, options, setup. Click on meshing. Now we're gonna create lines. We go here, we go to line, and it's gonna ask us where do we want to create our lines. It's gonna be line 1, and we want to create it 2 inches away from the cylinder. We know that we want our C because C is not gonna influence. We want it at 0, 0. Our Y, this is gonna be at negative 15 and 15. Let me just double check our geometry. Sorry, this is our geometry. It's gonna be 15 and 15. So if we have our X at 15 and our Y, sorry, and our Y1 to negative 15, we have it 2 inches and we create it. Now let's show it. You can see now that the plane has been created, the line has been created. Let's erase the symmetry wall so we can see it a bit clearer. It's just that this plane just, never mind, it doesn't give us a better visual. So one of the lines has been created. Let's create the other one. It's going to be 2 inches away from this one, so it's going to be 4. Create. I forgot to name it, but we have it here. And let's create another one 2 inches away from this one. It's going to be 6. Create. We can close this. Save and display. So you have our 3 lines. So we'll go to results. We click on plots, XY plot, setup. And we want our velocity. We want our velocity plot at line 1. And we want it, this is going on the Y direction, normal to the Y direction. So we select Y as 1. We can plot it. We can see our solutions here. Let's plot the other two. This is how they will look. Remember, if you just want this, just the results in as a vector, you can go to write file, and if you click on write, it's gonna save it as a document that you can open it on Notepad, and then you can copy paste it into Excel. For now, let's just leave it at this plot. So that's our velocity. We can go into our temperature. We can also go into our pressure. This is how our pressure is interacting in our body. And now we created those plots as well. Now we want to solve for the surface heat transfer coefficient and the total heat transfer rate. We'll go to reports. We'll click on fluxes. We want the total heat transfer rate at the cylinder wall. We can compute it, and it's gonna give us the answer here. It's 125, and have 125 right here on our console as well. So compared from the previous laminar flow, we had around 5, if I'm remembering correctly. So we have a huge increase in our heat transfer rate. So if we do the same for our surface heat transfer coefficient, we click on surface integrals, setup. It's going to be area weighted average. We want wall fluxes at the cylinder wall. But we don't want wall shear stress. We want surface heat transfer coefficient. Click on this. We have 56.52. That number compared to our last time, which we had 2.453, it's a huge increase on our heat transfer rate. Obviously, you can use a similar approach to what we did on our laminar flow problem to solve for the Nusselt number as well. We're not gonna solve in this on this tutorial, but that's how you will obtain all your solutions for the turbulent flow over a heated cylinder. So we obtain our contours, the velocity, temperature, and pressure. We obtain our plots, our surface heat transfer coefficient, and our total heat transfer rate.